Ivor, okay. Not only Ivor. That's even better. Now I'm stressed. Ivor is in the room. So this guy is famous for three things. Findbugs being one, Java Memory Model Crusade being the other, and new Java Memory Model being the third and final. Basically, he noticed that original Java Memory Model was badly broken. He noticed first one problem, then the other problem, then several problems. Then he started crusading with people who actually were behind the first Java Memory Model. And in a nutshell, he found out that even those people who actually authored the original thing, even they didn't actually realize how badly it was broken. So he started campaigning that we need something new, something better, something which actually works. How is it broken? I'll let you know in a second. Sarita Adve is the next person, one of the first persons who actually joined Bill Pugh's crusade. She's also a very prolific author about all things with memory consistency models. She is the person who actually coined the best definition of memory consistency model. So the intro is actually behind us. I'm talking about memory models, but so far I haven't yet told you what these are, so I'll do it in a flash. Then I'll talk about hardware stuff, and then finally the Java stuff. So if it's not about garbage collection, then what is it about? And the answer is memory consistency. It's about memory being consistent for every thread. It's about what threads get to see. It's about how we can actually optimize the code that is written and what optimizations are allowed. It's about possible behaviors and rules for those behaviors in multi-threaded programs, in concurrent programs. And it's about what is seen. A formal specification of how the memory system will appear to the programmer, eliminating the gap between the behavior expected by the programmer and the actual behavior supported by the system. This is the best definition of memory consistency model. So far, is it clear? Cool. Half of the room answered, half of the room went silent. That's not bad. So what actually memory model specifies? First of all, thread behavior. How threads will interact with the system. What value will a read return? If you actually do the variable read, what value will you get? When you update the value, when it becomes visible to every other thread that can actually get the value. And finally, what assumptions are allowed about program order and memory when you write a program and try to actually write a program that will optimize other programs. Examples of programs optimizing other programs? Sorry? JVM, yes. Namely compiler, namely JIT. Yes, very good. So this is where it matters. If you write your code, you'll see that you start with source files over here, be it in Java, be it in Python. Then these are made to the bytecode, intermediary level. Then the JVM takes over whatever JVM you're actually using. So with this, it only here gets executed on a physical hardware. And why this slide? Because this is the first point where your code can get reordered, optimized, where parts of your code can get removed. This is the second place. And of course, this is the third place. So there is a number of places when your code can get totally changed, all for performance. Now, Java Memory Consistency Model, or Java Memory Model for short, is actually a first language memory model. Before, people used libraries for threading, libraries like pthreads. Anybody here used pthreads? Free hands. Wow. Okay, hardware. Why hardware matters, how hardware can actually affect what gets reordered. So basically, the instruction sets, this is number one. Number of registers, this is number two. Caches, their size, their type. Actually, trying to fit the code in the cache line is one hell of a topic, which I will not delve into here because 15 minutes are nowhere near enough. How many functional units you have? Can you use GPU as well as CPU? Do you have anything else? In a nutshell, when it comes to hardware memory models, people who actually construct the hardware like things in terms of a pipeline. So first you have to decode the instruction, then you have to actually address the decode, then you actually go and do memory fetch, and so on and so on. With this, this is the crucial step for any hardware memory model that you will come to find. Examples of optimizations. Actually, these here are most prominent. So you get to reorder the code so that one thing gets executed quite ahead of where programmer wrote it and put it in the code. Prescient store is something that quite helps with that. And prescient store is also one of the earliest findings that Bill Pugh found that in old JVM, prescient store actually doesn't work. To remove what's unnecessary, for example, one of the biggest gains, if you can deal away with synchronize, then you're really, really ahead. Synchronize is one of the most expensive instructions you can get in Java. If you can shorten the machine code, if you can shorten the code, actually roll out a loop, get rid of a loop, number of optimizations exist. These optimizations can be performed on the JIT level, on the compiler level. They can even be performed even much lower. Perhaps you noticed already that I talked about hardware memory models and software memory models, namely language memory model, the Java one. If you wonder if they do clash, yes, they do. Exemplary CPU. If you take a look here, you can store your variables in the memory. You can store them in level 3 cache. You can store them in level 1 and 2 caches. Just going even further, you can store them even in the registers. Of course, this is the slowest, this is the fastest. Here, everything sees your variables. Here, only this very core sees them. Now, how do you think we may get things from here visible to this very core? I hear some answers, but they are very faint. You don't have microphone. Synchronization between caches, yes. Now, how do we get that synchronization? And that's actually a very awesome topic in itself, barriers or fences. These are actually machine instructions. And once such instruction is encountered, a number of protocols sprang to life, exchanging the information between the caches. Now, how those protocols work is a really intricate and very nice topic. I strongly encourage you to read at least one paper about that. It will really broaden your horizons. Start, for example, with the Lumesse protocol. And unfortunately, these instructions differ per architecture. Fortunately for Java programmers, JVM takes care of this stuff. So, in a nutshell, how it works. We put such instruction, and each time we do that, when it's encountered, it means flush the cache now. So the cache gets flushes. Once it gets flushed, the updates start to be exchanged, and what was, for example, sorry, let me go back. What was here gets transferred to here, perhaps even further, depends on the architecture. In a nutshell, it gets visible. Barriers come in 3 types. There is write barrier, read barrier, and full barrier. Of course, barriers are hell of expensive, but they are also atomic instructions. Do not read that slide. That slide is just an encouragement for you. This is actually all that is written in Java language specification about memory model. And this is what it actually means. So basically, if we were to summarize the JLS, it tells us that a memory model, if you ever try to implement a JVM, it should actually tell you what kind of optimizations are allowed, whether the execution trace is legal or not. Was that a question, or were you just waving? Just waving, OK. So he was waving for you. It also tells you that it works by examining each read, and it works by checking that set read, whether actually it checks write that is observed by the treat. Is that clear? Wow, I didn't mess it up, thank you. So it also makes sure that write follows certain rules. And these rules are very interesting. If you would like to know what rules, then the answer is before tiger or after tiger. And this comes with JSR 133, which is the result of crusade done by Bill Pugh. And the crusade was actually an enormous success. The things here are taken straight from the JSR 133 frequently asked questions page. And basically, it tells you a number of things about memory models. It's an excellent first step to actually learn about this stuff. Pugh, Manson, Getz, and others compiled a number of things for you to understand why memory model matters and what actually you can do about it. Each of those links has a short description of the problem and few facts that you need to actually know. So out of these, we have already covered most. And let me just briefly tell you about those we haven't. So do other languages, like for example C++, have a memory model? Well, they didn't at first. But seeing how successful Java was with its memory model, they started. So there are works on Python memory model, C++ already has the memory model in version 11, and a number of other things too. Actually, what else? There are nothing really of the basic stuff here, but if you're interested in learning more and can stay after, just stay. Reordering, a classic example. So, a question, where the comment is, with Polish word tutaj, which means here, what do you think the answer will be? Yes, there is at least one person who follows my presentation. Thank you very much. And there is at least one person who's not afraid to answer. Also good. So, yeah, the answer precisely depends on what kind of optimizations are allowed on the JVM that will execute that particular code. So, in a nutshell, why was the old Java memory consistency model broken? And the answer is very simple. You took a look, read the entire specification, and then was left totally to your own devices. Like, I don't understand. So with that, pretty much everybody who actually went for implementing a virtual machine, they did it differently. So what was allowed on implementation number 1 was totally not working in implementation number 2. Optimization could work here, but couldn't here. Some machines actually had the prescient store done much earlier than others. And there, the Java memory model worked even differently. So the new memory model, what it brings to the table. Final, volatile, synchronized. These are actually 3 keywords in Java language that make you use the barriers behind them. So to ensure visibility or to ensure that the variable will be only in memory, so will be visible at all times, these instructions carry with them a number of barriers inserted before or after, it depends on the context. So, store fence after write, load fence before read. That is volatile. Why? To answer that, just ponder what volatile actually does. Or actually a helper question. Who here used volatile? Awesome. Awesome. I never did. I never did use volatile unless actually I was curious, but it didn't yield much results then. So you're starting to answer.
So it ensures that we write before read?
Yeah, pretty much so. It ensures that whatever we actually do this way will get updated pretty often. Because notice, if we go back to the CPU, which is quite some slides behind, if my variable lands here, pretty much I can access it if I'm core 1. If I'm core number 2 or whatever else, I can't access it. So there are cases when you do not want that to happen. And of course, the problem is that if I can input my variable into my register, then I can access it like that. If I can input it in the caches, I can access it like that. And if I input it in the memory, I can access it.
Not that. Sometime.
Wait for it, wait for it. Yes, you did it. So these are the problems. So final, store fence after after init actually. Why? There are 3 people who started talking something.
Because after initializing, this variable will never change. So we put store value after initialization.
Yes. The problem with previous memory model was that occasionally your final fields appeared as if they changed value. Why would that be? Louder. Some threads didn't notice that. Okay, why? I can't hear you. Yeah, and because of one more thing.
Because updates from cache of your threads don't go to the main memory where each thread is accessed when reading. So this cache, this variable will only cache for first thread. That's all.
The final problem was also the fact that you could have initialized your variable with something else than the default value. If you had done so, one thread could actually get to your variable before your initialization actually happened. With that, your initialization, which actually gave your value, say, non-default, was too late. So first thread who got to your variable started operating on something else entirely. That's why final was broken. Was it something you wanted to say? Sorry, beat you to it this time. Okay, so if you would like to learn more, why actually memory consistency model is better than a threading library? The short answer is because it's built in the language. If it's built in the language, it actually aligns itself with the language. It gives you all the things that you need. That is why synchronized keyword is a keyword. If you would like to read more about it, there is a very nice paper by Henrik Bem, and there is a number of papers by Sarita Adva. What can you do to actually make memory consistency model better? Because current is good, but nowhere near flawless. If you would like to read that, I recommend to you works by Sarita Adva. Next idea, possible optimizations and the gains. Also, Sarita Adva and her students. Performance of Java and hardware memory consistency models. I told you that they clash. How badly do you think it is? Extremely. Okay. Irina? Depends. Okay. Diosoft person? I got 2 this time. 3? No. No answer?
On the last conference in Moscow, I don't remember the name of this conference, some guy from Moscow said that it's quite not perfect.
It's quite not what?
Perfect.
It's quite not perfect.
And truly hard to understand.
Okay, it is. So, Ivar, your answer? He wasn't listening. Okay, so the recent studies that I got to shown that the performance detriments are quite negligible. First, let me actually tell you more in detail. Why would both memory models clash? The answer is barriers. Memory models need barriers to actually make sure that certain behaviors are guaranteed. So if I write hardware memory model, then I program my hardware, my CPU and all the other things to insert barriers here and there. Now, if I have Java memory consistency model, I don't need those barriers over there. I have my barriers built in. So I need to actually code around those barriers. I need to actually remove them or actually make them invisible. Is that clear? A very hesitant yes. So imagine it this way. I need my program to follow only certain execution paths. Every other execution path is not allowed. Now, imagine that you have a very creative team who actually created this PC architecture. And they want their programs to move along different paths than I imagined when I created Java. So now my program can be reordered in a way I, in JVM, told it's not possible. With that, strange results will follow. So basically, if the hardware memory model architecture allows for any such behaviors, Java, JVM for this architecture, needs to actually completely eliminate it, make it like it never existed, because JVM just needs to be unified architecture for everything. And thus, there is a need to insert or code around another set of barriers. And with that comes performance detriment, which is frankly quite negligible. So thank you very much. That is all.